Hello everyone. So we will deal with also on about execution trace, but in the DRM case this time, DRM analysis. So some months ago, we analyzed heavily obfuscated DRM code, and what we are going to show you is all the protection involved in this DRM and all the technique we use to bypass them. Quick presentation. So we work on this analysis at Quarks Lab some months ago with Camille mougey. He is now working at CA DRM in France now, and me, Francis, I'm still working at Quarks Lab for 2 years. So we'll speak about, of course, reverse engineering. To present the DRM stuff and our attack methodology. Then we will talk about execution trace that concern all of the collection of data of a program during the time, and then its analysis. And then code obfuscation, so the protection we try to fight, and our attacks based on this trace. I guess everyone here is used to obfuscation, but quickly, what obfuscation is, it's some procedures that make our reverse engineering work longer, harder, and more expensive. So we have some example of some basic protection like code flattening, data flow protection, or junk code that we encounter. So we think that binary obfuscation is like an onion, because you have to remove step by step every layer, each one making you cry a bit more. So to start with the DRM we analyzed, we saw that there was some network communication. So we looked up the packet content, and we see that there is a high entropy data in it. So maybe the presence of compression or crypto. And then we took our favorite tools to try to debug and analyze the code in static and dynamic way. So we see that all the control flow graph of all functions involved in the DRM were flattened, protected by code flattening procedure. And all instructions in all basic block of flattened function are also obfuscated with junk code and instruction substitution. So with classical tools, it's very complicated to analyze this kind of code. So I will present the first layer, the code flattening. As an example, here you have a normal control flow graph of a basic function with a loop and a precondition and the output. And here is the flattened version, and all the code involved in the DRM is like that. It's classical code flattening with a first basic block that is executed at the start of the function, and then we have a dispatcher that chooses the next basic block to execute, and then the code is executed, and the next basic block is set, the dispatcher jumps, and so on. And as I said, all code in each basic block is also obfuscated, so how to deal with this kind of protection? So here we found two possible approach. The first one is to study the protection itself. So basically, we can do some symbolic execution of the code to find the old path in the functions. So the advantage here is that you can reuse the tools that you have made if you encounter another program that uses the same protection procedure. But in our case, it was very too complex. We have to face with a combinatory explosion, and a lot of resources needed. So we are still working on it, and we also tried this kind of approach on OLLVM project that was presented yesterday, and also we will show you at the end of this talk some slide on this subject. And the other approach is to study only one execution, so by producing a trace. There is no more CFG because we are just recording one path to analyze. The main advantage here is that the code is very is easier to understand because we know that the output that we try to understand is produced by the code we recorded, so we just have to search to do some analyze passes on the code we instrumented. So what we did, we choose, of course, the execution trace approach. And what we need is to record the context evolution over the time. So basically the register states or register value for each instruction, each executed instruction, so all the code executed, and all memory accesses done by the executed instruction. Then we needed a tool to manage the execution trace we produced, and then we needed some module to access the execution trace data to extract, in fact, the relevant information. So here is the list of the context to deal with: the instrumentation, data collection, the database, so the efficient trace storage, and then processing, so the relevant access of the information. So we made a tool that we named Petra, and Camille will present you now.
Okay. Hi, guys. So what is Petra? It stands for Python Trace Analyzer. This is, as Gigi said, execution trace management framework. So we want to provide an API to just manipulating trace, do some requests, and it has to be so fully modular to be used with external tools, and scalable. So for instance, our DRM trace is about 100 million of instructions and half memory accesses. So we want to have this trace in memory and be able to process some requests in an acceptable response time, because we want to use our tool, of course. And it has to be architecture independent because we want to use it on RAM x86 extra. So generally speaking, you just want to say, hey, I have an idea and I want to make a proof of concept, test it, and if it works, I will do some things clean. So just a few words of an implementation. It's layered, it's modular. You get the analyzer parts, which is the part which query database and output some information. You got the parser to manage the trace, external tools to, for instance, this assembly one, this assembly engine, etc. And actually, the code isn't yet open source. But if you want to reproduce them, we write a big paper on STIC 2018, and we even do a UML memory model in it. Yeah, we actually do it. And so choice of implementation, we choose MongoDB for scalable, and because we are lazy and it's very easy to use and to prototype with it. We got a database per trace because we don't want a MongoDB lock, and we want to be able to do some hypotheses on the entries. So, for instance, we said if we have two entries with the ID1 and ID2, the entry with the ID2 has happened in the time after the ID1. For the execution trace, we use Intel Pin, but we can also use MyAssam Sandbox or HIDA or LiDBG extra. And for this assembly engine, first we use the DiceStorm, and then we switch to MyAssam to be architecture independent and to obtain directly an intermediate representation. Okay, so just a few words about MyAssam because we use it a lot in our code. It's been developed by Fabrice Desclos. The version 2 has been released just months ago, and the main difference between the version 2 and version 1 is that not just only Fabrice can use it. I also develop on it. and it's available on Google Code. So it's composed with a Python and assembly. The assembly engine easy to write. So when you write your assembly, you automatically get the disassembly engine. You get then an interpreted representation, which is reverse oriented, just a few words, and a Jite engine based on a tiny CC, LLVM, or just Python. And we even got a regression test. So what are the architectures supported? We have 86, x86, AML, RAM, the MSP 430 for the micro corruption challenge, of course, SH4 for fun and extra. And then we got two customizable simplification engine. When we get some expression to simplify, we just add it and it do some stuff. You can parse, you can sandbox some binaries. We have to rewrite Windows architecture independent to manage some APIs and to update our sandbox, simulating the function impact. We use the help scheme to manipulate the binary, which is like Scapy for binary, and wrote by the same guy, right by the same guy. And it's linked with some other tools. So just first demo on the shellcode. So we got our shellcode here. It's just ASCII 1. And okay, so our shellcode. First, we just build a PE with to use with other tools using elf steam. Then we got our PE with our shellcode. And then we will use the MyAssem sandbox to emulate the binaries with a try and die approach. So just say, okay, run the DPE, and then it crash. Okay. So what's happened here? Actually, you can see this address is not in virtual memory, and we see the file segment. So for guys who are doing malware. So we tell to MyAssem to manage it. Okay, not this one. And we crash again. But this time it's because it tried to browse the DLL list. So we tell it, okay, so now import some DLL. You can see them. And then it run, and it crash. So again. Why? This time it wants to call this function. Actually, when MyAssem is launched, and when he parse DLL, he wrote on a paper, okay, at this address I put this function, at this one extra, and so on. And so we just have to simulate this function. So what we actually do is, okay, so just we just say, okay, add this function. She's doing nothing. We just say, okay, there is two args. I don't know if you can. Okay, two args, and just return one. So actually nothing. And then it runs and crash again, but on another function. So I think you get the point. I just had just a few other functions, which are create process, URL download, and quick implementation of printf. So we launch it. And we got a URL download to cache with a this URL and a create process after. So this is to show you how we can okay, not this one. How we can just have a sandbox and control all the impact of a function. And actually, we also control all pointer, all page management. So if we do two trace, with the same code, it's completely determinist, and the trace will be exactly the same. So if you do to trace by modifying just 1 byte in the input, the only difference will be the result of this modification. And second demo quickly to show you a case on ARM. So what we got is just we simulate MD5, and we got the general purpose register at each time the instruction executed and memory access, like this one. Okay. So you will continue. Back to the DRM case.
Okay. So now back to the DRM. So in introduction, what we want to know to try to understand all the DRM codes is to fully understand an algorithm that produces a block of data, potentially some crypto or compression, and to understand what is inside, so all encryption function involved in it, and all derivation of data, etc. So what we can say is the Petra database contains all we need because we instrumented all the code that produce the block. So how to proceed? We have to identify all parts, so all functions, the input and output of all of these functions, and understand the link between them. For example, the encryption key, the data which are processed, and so on. The first attack we did is constant detection, so it's very classical in this field. You know that some cryptography algorithm have some matching constants like hatching function, for example. So if an algorithm is present in our trace, we will find its constants. So where we can find them, so the interesting places can be in the instructions themselves. It's more like static analysis. It's like a move instruction with the constant in a register. But if the program is obfuscated and, for example, we search for the 4 constants, the program can make move 2, and add them. So we cannot find them in the instructions. So we have to research for it in processor registers, and also memory access. Why not? Again, Petra provides all direct access to all these elements. So we have to just to search it. So in practical, our method is to add a module to Petra. It's a simple Python script where we wrote a list of constants and the algorithm associated, and then we do a full research in Petra database for this constant. We didn't found any false positive, but it can happen. But we think there is a low probability for it, and if you have some false positive, you can remove it by grouping the results. So we remove isolated constant. So it's a very simple, quick, and efficient method. The results, we found a Mersenne twister identification with its constant. It's a PRNG. We also identified the 5 constants of the SHA-1 algorithm by finding its 5 constants. And all we have to do then is to add the SHA-1 primitive knowledge in our call graph. So I will make a little demo here using Petra. So here is the main Petra interface. For this example, we imported a trace of the IS computation on the same DRM. It's not the SHA-1, but an IS white box algorithm. On the first page, we can say some information about how we collected. And here we will focus on the call graph. So we have some tool here. And if we access the call graph, we have a list of all functions we are instrumented. So it's basically a tree. We can access the number of instructions that are in each function, and we can command them. For example, if I click on this function, I can rename it, etc. So if I guess that this function is a SHA-1, I will rename it, and in all my call graph, all the functions that are involved in SHA-1 will be also renamed. Okay. Next one, we needed to identify inputs and outputs on a function. Basically, for the SHA-1, we needed to know if the output data of the SHA-1 function is really the original SHA-1 value, and to check if it's not modified. So we have to do I/O identification. So for unidentified function, it can help us to identify them, because if we have the input and output, we can do some guessing and find the purpose of the function. And if we have already some identified function, typically like the SHA-1, it can help us to find the arguments where they come from and do the link between the other primitive of the DRM algorithm. So what we know about the input and output by studying memory access on a function. If a data is processed by a function, the input will be read, and all results will be written in memory. Again, Petra can help us to find them, because we instrumented all memory accesses of the DRM code. So to identify outputs, what we did is to a memory diff. So we take the memory state after the execution of the function minus the one before. Also, we can remove the data that are written but read again before the end of the function, because it can be temporary data and not really output. And to identify outputs, just we read the data that are read the first time by the function. Then we can add several heuristics like pointer detection to avoid analyzing useless data, block grouping to reconstruct pseudo variables, and entropy computing to have some information about some crypto data and so on. So the result of this method, it's, we think, a very efficient method to find algorithm, to link algorithm between them. And thanks to that, we found another protection by looking for an input and output of all function. It's transform memory. So in fact, the DRM code never writes the data that it proceeds in clear format in RAM. It is derived by some computation. We didn't identify a pattern in code to break this kind of protection. So it was very boring. We have to find each computation that were applied on each block. And the only thing we managed to identify is that there is derivation function per memory area. So in one block, only one computation will be applied. So if we find the transformation of one byte, it's all the block that will be the same. Some demo of memory diff. So I will take as example the iOS 1 because it's more interesting. So here we identify, Camille will discuss of the iOS later, but here we imagine that we don't know this function is the iOS core. We can click on it and do a memory diff on it. Here we have prepared the demo, so all the data is in cache, but here in the top we have a scheduler to be able to do a memory diff in the background and be able to work while the memdiff is computed. So we have access to some information, the memory read and the memory what is written. The heap parts in blue and the stack part in green. We have the address of each block. Data are grouped by memory accesses, so typically here it's a 4-byte memory read. We have the ASCII dump, the size of the block, and the compression rate. So here, as a demo, I take a block that is written. So here we can see that it's a big block that is accessed by the same instruction, but byte per byte. The block have a big size and the compression rate near to 0. And what we can see at the end of this block is that there is the same value of DD that is repeated. So typically for the AES, it's the padding, but in general the padding is 0, not DD. So that's why we found the data was transformed. And for example, we have some interesting functionality like clicking on a byte, and we know the memory access in database, the instruction that do the write. We can do go to the instruction that have written this byte and so on. So the identified algorithm. So we managed to check that thanks to this method, the SHA-1 input and outputs are the good ones. So SHA-1 was fully identified, and we had the knowledge to our call graph. What we've seen is that the SHA-1 inputs were certificates. So basically, it was a certificate chain validation. And by looking at the certificate, we see that it was a RSA and SHA-1 signature algorithm. So we have to identify in our trace the RSA algorithm in case it was reused. It's pretty important. So what we did to identify the RSA function, the main idea is to destroy the modular exponentiation computation of RSA and compute another execution trace. Here are the steps. So we know that the RSA algorithm is used, at least in the search and validation. So we patch all our certificate public exponent to 1 to avoid the effect of exponentiation. We patch all certificate public modules to the max value. So there is no modular exponentiation, and then we produce again a new execution trace, and we just have to compare the two traces in terms of number of instructions, and we located the function that has 50 million instructions less than the other. So we located precisely the place where RSA was computed. So then we add the RSA knowledge to the call graph, and the RSA function were indeed reused in the DRM computation to do some algorithm like RSA OAEP. And now Camille will present some other attacks we did.
Okay, then to clearly understand what it's doing, we use some data slicing and data tainting. So just remind the data tainting, it's when you follow all the elements that depend on a given one, and the slicing is the reverse algorithm. You find all elements influencing a given one. So as we got a trace, we prefer to use the data slicing. It's really it's more interesting because in this protection, to avoid data tainting, guys have duplicate each buffer, then duplicate them again. So data tainting completely explode. But when you're doing slicing, you're beginning from the output, and you just have one path to go to the input. How we manage this using MySM again? So we use the symbolic execution. We begin at the beginning of the basic block containing our targeted element. We execute to the instruction containing our element, and we got the equation depending on context at the beginning of the basic block. Why the basic block? It's an empirical result. It's clearly a good one. Then when we got the dependency, we continue by finding the last change and apply the algorithm again. And for data tainting is the inverse. So slicing as a commercial. So when we go from we begin with a memory access, and we say, okay, so what is access has been done. So we ask to find the dependencies and the equation. So we got the memory access equation and all its dependencies. So it is octet memory access and byte memory access, sorry, and then on a double word. Extra, and it depends on tools one. So we just have after to develop each part of our our tree. And recursively, then we can link outputs with inputs. At the end, when we begin from the block that have been pasted to the RSA. It is block 1 and block 2. And as we know, SHA-1 and the Mason twister, which is used to produce 3 random values, we can compute this dependency graph. And actually, this is RSA or AEP. So then we move on in our second data or network on the network. We apply this algorithm again, and we got this dependency graph. So it looks like crypto, but for C1 to C3 we got a derivation, and we got all of this S table, substitution table, which are applied before using the XOR and before go to the output. So we got an ID. We say, okay, in a function, in a parsing function, when there are 2 data in tree, there's a big probability that the same instruction will parse them. So, for instance, you get the instruction that will parse the length of the data, then the instruction that will that will compute the the buffer, and then the padding, extra. And so we say we will regroup this instruction by classes when they are computed by the same instruction. Actually, what we obtain commonly is a pattern in class. So, for instance, 1, 2, 3, 4, 1, 2, 3, 4, and so on. And this is because in just a loop, there is a first instruction to read the first byte, then the second, and the 4, extra. And when we get that, we regroup to the bytes this way, and the last is in another place. So applying this algorithm to our entry give us directly this structure, and we got three main blocks, 2 of 6 bytes, and the last one composed by the 16 bytes. If you remember the first graph, it's like the C1 and the 2 blocks in C2. Then we apply the reversed algorithm on beginning from outputs that Gigi showed to you with DDDDD padding, and we search for the last write, and we got this structure. The first 2 bytes are used, I think, for length, then a group of bytes, and then DDDDD, which are write but never read. So if this is really padding, that's a problem. So then you use the data slicing equation to rebuild the equation of the C3 components, and we got this one. But this one, actually, if you look at the AES key expansion algorithm, you can see that S table that are used are actually standing for SBox and REcon algorithm, and so there are some clues that we are pretty sure that this is AES algorithm. So at this stage we say, okay, so this is AES. We'll take the input, paste in our algorithm, and try to match the outputs. It did not work at all. Actually, there is some encryption steps that are used, and the whole algorithm is done on modified states. In other words, the raw data are never unclear, even in a register, never in memory. So we call it a white box, and because the key is also a parameter, we call it a dynamic white box. Why there is this one in DRM, so clearly to waste analysis time, and it's a good way to hiding inputs and outputs because we never know it. And if you want to reproduce it on another device or system for interoperability, or I don't know, the only solution is to rip it. And we cannot, in this case, use the decryption algorithm. We just have the encrypt one. So how do we manage it? Actually, in AES, apart mixing colons, the only operation that is made between bytes is XOR. So the derivation has to be homomorphic to this operation. So it is import a lot of properties on derivation mathematics properties, and there is only a limited set of candidates that can match. And then, because of the complexity of AES, we got a lot of restriction on those candidates. And we finally be able to read and alter values that are used by the algorithm, which is actually AES CBC. Okay, last one, the instruction substitution. So basically, I think that everybody knows this. We begin with this kind of function, and we say, okay, we will just modify constant, add junk code, etc., to obtain the second one. And this is very easy to simplify thanks to constant folding. Compilation passes are very effective on this. But what we found in the DRM is what we call MBA for mixing Boolean and arithmetic transformations, which give us this kind of identities. And actually, this kind of identities aren't simplified by compiler bases, but aren't simplified too by MATLAB, Maple, Mathematica, Z3, and so on. Actually, these tools try to convert this problem to SAT1 and use a solver on it, and it just failed. So how we manage it? The guys who were doing the protection just have a small set of to their identities, and then when we identify one, we add it in a MySM simplification engine, and so when we compute the data slicing and equation, etc., this is directly simplified. We also find some algorithm to generate that kind of expression. I'll just show you one. So just a bit of mathematics here, but it's quite easy. We use just a matrix and its associated vector. The matrix is in the base GF2, that's to say x, y, x, y, sorry, x XOR y, not x, not y, etc. The v vector is composed only by 1 and -1. And we can say an equation is valid and generalizable to 2 power n if and only if there is a linear combination that is equal to null elements. So for instance, if I take this expression, the equivalent representation is that is 1. So with the first column that is representing x, the second that is standing for y, and the last one for x XOR y. And we say, okay, this is plus, plus, and minus. This is the v vector. And how it works in a simplification. Actually, the simplification algorithm and the identity generation is the same. So if you want to simplify this expression, which is weird, we compute its representation. So this one is for x, this one for not x, and so on. The plus, plus, minus, etc. We compute the linear combinations of the 2 is the 1 plus 1. Here we got 1 minus 1 for the 0, etc. And what we want is to nullify this combination, this linear combination. So we just have to subtract with 1, 0, 0, 0, then 1, 0, 1, 0. It's what we do with this matrix and V vector. And this one is actually not y, and this one is actually not x or y. So we got this final equation, which is valid for 2 power n. So if we just pass these two elements to the right, we got these identities, and we can simplify our expression. But in our DRM, it's look like this. So you got the code flattening, the Gen code, etc. We produce the equation of the result, depending on the only one input. We got this. We identify a variable and constant folding, extra, extra, and then actually it's just XOR with 5C. For HMAC, of course. We find the same things with 36. Yeah. So your device is doing XOR, and you just lose a few % of battery. Just some bonus, because you got time, yeah. We managed to graph memory access over the time. So here you got the memory addresses, here the time. And so the first column stands for the binary or data. The second one is the heap, and the last one is the stack. And then by zooming on parts which are corresponding to a known algorithm. So for instance, we got a big one with a very big basic block, and we don't know what it is doing. And when we zoom on memory accesses, we clearly detect a loop that has been unfolded, and a loop with 32 iterations. If you look at the heap, it's exactly the same with the read of a group of bytes. This is the noises due to the code flattening and the context updates. And at the just beginning, we see some inputs that are read, and some data that are written, so for the output. So that's a pretty good way to identify some algorithm. And another slide on LLVM obfuscator that I've been talking yesterday. Why LLVM? Because it's open source, it's a recent project, and a lot of people are talking about this. So what are the protections that have been implemented in it? There is the instruction substitution, but a very basic one. So for instance, instead of A plus B, there is A plus R minus R plus B. There is some opaque predicates that they call a bogus control flow, but actually there is only one. And they managed to add code flattening. So this is the initial function, an addition with the conditions, very basic one. And we compute the code flattening. Actually, it's not very graph flattened, because they aren't using a jump table, but a succession of if-else of a conditional jump. Then we use the symbolic execution. And from the beginning, we obtain the first context. We go to the right basic block. The context is updated in symbolic. We find the second one. When there is a condition, we split the symbolic execution and continue on the first one, then on the second. And what you obtain at the end, you obtain this graph, which is actually the same as the first one. But we aren't able to. I think that you can see, but this is a jump and not a conditional jump, because actually we aren't able to say this is this condition, and we need to use some STP solver extra to manage it. to answer to a question that has been asked to Maxima guys yesterday, the instruction substitution is clearly done. It's clearly simplified by OLLVM basis. So
in conclusion, what we can retain of our approach is that allowed us to analyze state-of-the-art obfuscation mechanism in the DRM. For us, it's just one more method in the analyst toolbox, but it can be reused for other cases like malware analysis or even vulnerability research. About the obfuscation, we can say that nowadays more and more obfuscation are used, and it's more and more complex. Camille presented OLLVM, and we tried that because we wanted to compare, in fact, in what we have in our DRM and in OLLVM, but we think that OLLVM is still too young at this time. We can say also that nowadays devices, even the mobile ones, are got enough resource to execute some code like the XOR that we've seen before. So it can be they have enough resource to write them. So to conclude, our approach is not better than another. It's just another way to proceed. So thank you.